Okay, first an announcement. So I just got approval from the university registrar's office that we can continue teaching this class throughout this quarter remotely. So we will do that. I think the primary reason from my perspective is that I hope the recording quality can be better if we do it this way instead of going to the classroom. Because if I write on the blackboard in the classroom, the recording quality will be worse. So it will be much harder for you to read what I write down on the video, in the video. So virtual for the rest of the quarter, yes. So we previous announced will be virtual for week 5 and week 6. But the new announcement is that we got approval to continue doing this for the remaining of this quarter. So basically the midterm and the final will also be remote. So I'll try to make that possible for everyone. So that's the current plan. So if you have any objections or suggestions, please feel free to let me know. Okay, so that's the announcement, and I will make a formal written announcement on CCLD after this class. So first of all, we will continue our discussion. Last time, we introduced the chi-square distribution. This is not an X, but a chi, okay, a Greek letter. Yes, I said the whole quarter. So for the chi, and also for those of you who want to ask questions, it will be great if you can show up, just like we have two faces here. So then, yeah, I think it will be more interactive. Okay, thank you. So yeah, those are the familiar faces. So especially we're going to do this virtually, it will be great that I can at least see you virtually so I can see who I'm talking to, right? So we introduced the chi-square distribution. There's only one parameter called the degrees of freedom. So later we will see why this can be reasonably called a degrees of freedom. Okay, so some important facts about the normal distribution and the chi-square distribution. So first of all, the chi-square distribution is a special case of the gamma distribution. And you can also think of the chi-square distribution as defined as the distribution of the squared standard normal random variable. If you have a standard normal random variable, you square it, then the square will follow what we call chi-square 1. And for chi-square n, you can think of it defined as the sum of n IID squared standard normal. So you have n chi-square 1, and they're independent. You sum them up, then the sum will follow chi-square n. So that's the way to think about the chi-square distribution. And you may wonder, why do we want to learn about this chi-square distribution? So as I said, this chi-square distribution is manually created for our own convenience to describe the behavior of sum of independent squared standard normal distributions. So two important applications of the chi-square distribution include what we call the goodness of fit test and the independence test. So we are not introducing them for now, but these are very commonly used tests in statistics, in applied statistics. For goodness of fit test, it's about if you think about your data and you try to ask a question, does my data fit a normal distribution well? If that's your question, then you could apply the goodness of fit test to check if your data fits normal distribution well. And for the independence test, it's like if you have a 2x2 table and you want to know whether the row variables and the column variables are independent. So for example, let's say our two rows indicate admission, not admission, and our two columns are the applicant's gender, male, female, and you want to know whether the admission decision is independent of the gender. In that case, if you have that 2x2 table and each cell is the count, like the number of male applicants that are admitted, the number of male applicants that are not admitted, the number of female applicants that are admitted, and the number of female applicants that are not admitted. With those 4 counts, then you could perform the so-called Pearson's chi-square test. to check whether you can decide the gender and application decision are independent or not. So these are two applications where we would use chi-square distribution. So that's why we're introducing it here. Okay, and so before we resume what we said last time, I want to give people some important facts that maybe as a recap about the special properties about normal distribution. So I'll leave some space here, but I'll return to this, the leftover problem from last time. So some important things about normal random variables, just for everyone's information, so we can, again, try to keep everybody on the same page. So first, let's say that we have Z1 to Zn NIID standard normal random variables, right? So given that, so one important fact we know is that the expectation of each Zi is 0. The variance of each Zi is 1 by definition, the standard normal distribution. And some important properties or consequences of this is that first, if we take the sum of those Zi, we would know that the sum would still follow a normal distribution with mean 0, and the variance would be the sum of their variances, so it will be n. Okay, this is about the sum. And the second thing is about the average. If we take the average of those Zi, take the sum and do the division. So we denoted this by Zn bar. This is a notation we used. Then this will follow also a normal distribution with mean 0, but now the variance is not 1, but 1 over n. So this is something everybody should be able to derive now. So the distribution of the distribution of the mean. And basically you can see that an important property is actually if we increase the n, and in our statistical context, this is the sample size. If we increase the sample size n, we will see that this is called sample mean. Sample mean will actually have a diminishing variance. The variance 1 over n is going down to 0 as n goes to infinity, which means that the larger the sample size, the less uncertain the sample mean, right? So by uncertainty here, again, we're talking about the repetitive sampling uncertainty. So that means this Z1 is a random variable. It can draw any value from standard normal, and Zn is also the same. So therefore, when I do the sampling for once, I will get n values and I will get an average sample mean. And this is called one realization of our random variables. But if I repeatedly do the sampling, let's say I draw Z1 to Zn independently from this normal distribution for 1,000 times, then I will get 1,000 mean here. And these 1,000 means would follow this distribution. Okay, but as I said, that this 1 over n variance is going down to 0. What it means is that those 1,000 values will become more and more similar if this n is getting large. So that's essentially what this is saying. So, and if, I don't know if you learned this from 108, but I'll just say that there's another important result in probability called the law of large numbers. The law of large numbers is basically saying that the sample mean would converge in probability and also almost surely. So I'm using those more advanced words about different types of convergence. But basically this mean is convergent to the mean, the sample mean is convergent to the mean 0 as n goes to infinity. That's all we call the law of large numbers. So basically, let's say you expect this to be around 0, right? But if n is very large, then this average maybe will become closer and closer to 0. So like it can be 0.1, negative 0.1, they're very close to 0. And when n gets larger, then the distance between the sample mean and 0 will become smaller. So that's what the law of large numbers is saying. Okay, so I try to say that given we have IID standard normal, the sum is also normal and the average is also normal. So now let's talk about square. So let's say 3. For the square, sum of zi squared. So this is following what we call chi-square distribution with n degrees of freedom. Okay, now I'm going to introduce some important properties about the chi-square distribution. What's its mean? What's its variance? So unlike the normal distribution, it's obvious, right? This is the mean, this is the variance. The distribution itself specified by the mean and the variance. For the chi-square, we can write its mean and variance in terms of the degrees of freedom. So basically, in this case, the mean of the chi-square n is n. And the variance of a chi-square n random variable is 2 times the degrees of freedom, so 2n. So these are also nice properties about this distribution. So basically, from this, you can see that as n goes large, the degrees of freedom increases, then both mean and variance will increase. So you can imagine what the shape of the distribution would be like. So it would be, so for example, let's say that and the chi-square distribution is defined on the real part, on the positive part of the real line. So when n is small. So let's say this is the PDF of chi-square n, the density function. So when n is very small, probably the density curve will look like something like this. It's not symmetric, okay, unlike the normal distribution. But when n is large, then the density will shift like this. So you see, both the mean is shifted to the right, and also the variance is becoming larger. So you have a wider spread in your density curve. So that's the thing you would expect for a chi-square distribution. Okay, so I'm using this just as the standard normal case as a starting point. Now let's move to the more general case about any normal distribution. Let's say x1 to xn are IID general normal distribution with mean mu, variance sigma squared. Okay, then for the 3 properties we wrote there, so the first one is if we still take the sum of the xi's, the sum would follow a normal distribution with the mean as n mu, n times mu, and the variance as n sigma squared. And for the average, it will also be normal. The mean will stay as mu, the variance will be sigma squared over n. Okay, and finally, for the squared form. So now, if we want to make it chi-square, we need to standardize each normal variable to be standard normal. So here, this result will be xi minus mu divided by sigma squared. All right, I standardize each xi before squaring it, and this will follow chi-square n. So these are the results we would obtain from the general, to be generalized from the above. So I will leave those for your own verification. Try to make sure that you know how each one is derived. Does the chi-square distribution approach a normal distribution? Very nice point. Yeah, that's the thing I wanted to say. So Brandon, you made a very good point. So basically, based on this result, right? Let me just continue writing here. So let's say that in this case, we just come from here. So we have z1 squared to zn squared. Because z1 to zn are IID, standard normal. So z1 squared to zn squared, they are IID chi-square 1, right? Then, because each one we know, let's check the condition of the central limit theorem, because each variance, the variance of each zi squared is just 2, which is definitely finite, right? So it's not infinity. So which is finite. So by the central limit theorem, we indeed would have the sum of zi squared be approximately normal, okay? And then we can say that minus its own mean. What's its mean? This follows chi-square n, so the mean is n, dividing its variance square root. So basically the variance is 2n, we take the square root of it. So we will know this is approximately standard normal by the central limit theorem. So indeed, so if I can do this in R, and you can use the code I provided in R. So basically, if I draw IID from chi-square 1, when this sample size n gets large, and then I can do this calculation of its sum of the square of sum of the chi-square ones, then we can see gradually the distribution of the sum will be more and more like a normal distribution. So basically from this CLT result, central limit theorem result, we can equivalently write it as the sum of zi squared would be approximately normal distribution with mean and variance 2n. Okay. All right, so these are the things I want to wrap up, right? As a way to summarize what we have learned. So you can see that intuitively or roughly speaking, we will think of the chi-square 1 as the squared distribution of standard normal. Okay, so coming back to our last lecture, we stopped here. So what we were doing here is that we were talking about an important property of normal distribution, normal random variables. So we are saying that we have IID, normal random variables with mean, mu, variance, sigma square. We define their mean, and we want to show that the mean and the difference between each random variable and the mean, they are independent. So I said this is not something that holds in general, that somehow it just holds for normal distribution. So that's why normal distribution has very nice properties. So we try to show this, prove this independence using the joint MGF. So we just want to show that the joint MGF of this pair can be factorized as the MGF of this times the MGF of this. So that's our goal. So therefore, we spent some efforts to derive the joint MGF of xn bar and xi minus xn bar. And we got here. Okay, this is the MGF we have. And to derive this joint MGF, we use the fact that x1 to xn are IID normal mu sigma squared. So we use that. And also the normal mu sigma squares MGF. That's our condition. So this is what we got for the joint MGF. And this is what we have for the two marginal MGFs. So the MGF of xn bar is this, and the MGF of xi minus xn bar is this. So then we're just left to show that the joint MGF with this exponent is this exponent of the joint MGF can be written as the sum of the exponents of the two marginal MGFs. So we stop here. So I asked you to try to do this algebra yourself last time so that you can show they are actually equal to each other. So right here, I'm just going to give you a quick way to solve this algebra. So you can quickly show that the left-hand side is equal to the right-hand side. So one thing to notice is that, so for this term, it's mu times s minus t over n times n minus 1. And we also have mu times s minus t over n here. So this term and this term can be combined. So let's first try to do it. So for these two terms, you see, basically we have mu s minus t over n. I expand the first term plus mu t plus mu times s minus t over n times n minus 1. So you see these two terms can be combined as mu times s minus t over m times, this is 1 plus n minus 1, I get m, okay, plus mu t. And you see this n and this n can be canceled. So I'm left with mu s minus mu t plus mu t. So I got mu s. So that's how I simplify these two terms by taking the sum. And also for these two terms, I'm going to combine them. So basically, you see here I'm going to get this term expanded because I will try to get s minus t over n squared to be matched with the square term here. So I will do sigma squared over 2 s minus t over m plus t squared plus sigma squared over 2 s minus t over n squared n minus 1. Okay, for the first term, I'm going to expand it. So I will get sigma squared over 2 s minus t over n squared plus 2 times s minus t times t over n plus t squared. This is what I get from the first term. Plus sigma squared over 2 s minus t over n squared n minus 1. So now you see this term and this term, they can be combined. Maybe I'll just write it to be continue to the next page. So basically from here, so let's say call this star. So this star right here will be equal to, if I combine those two terms, I will get sigma squared over 2 s minus t over n squared. So I have a 1 here, I have an n minus 1 here times n. So I combine them. And I have 2 more terms left here. So I would have sigma squared over 2. Okay, 2 times s minus t times t over m plus t squared. All right, and here this n and there's an n squared can be canceled. So I would have sigma squared over 2 times n s minus t squared. Okay, and I have this term. So I will try to put the n out. Okay, so basically I will also have 2n sigma squared to be matched with the 2n in the denominator here. And here I have 2 times, okay, st minus t squared. And because I get an n out, so this one becomes nt squared. Okay, and then finally, I will try to combine the terms. So the common factor I can get out is sigma squared over 2n. And inside, I will have this s minus t squared, I expanded. S squared minus 2st plus t squared. And over here, I have plus 2st minus 2t squared plus nt squared. Okay, so finally, I can have some cancellations. So this one and this one, the 2st terms are canceled. And I have t squared minus 2t squared plus nt squared. So finally, I have, this will become sigma squared over 2m times s squared plus n minus 1 t squared. That's what I have. So therefore, you see, from simplifying the left-hand side, I have mu s matched with this one. I have the second one as sigma squared times s squared divided 2m matches this one. Finally, sigma squared times n minus 1 t squared over 2n matches this one. So therefore, I show that these two lines are equal. So that's what I didn't do last time, but hopefully, I hope some of you have tried to do this because this is the algebra we will need. Okay, so we prove it. So just to go back to the conclusion. So the conclusion is that so xn bar and xi minus xn bar are independent. This is the conclusion we try to prove, which is a special property about normally distributed random variables, x1 to xn. Okay, any questions about this part? Okay, so if not, then we will continue. So our next result is called a corollary from this theorem we just proved. So now we are going to define our sample variance as S squared, which is defined as 1 over n minus 1. So regarding why this is n minus 1 instead of n, we're going to show you later in this class. But let's just try to use this formula. This is what we call a sample variance. So we take each random variable, xi, subtract its mean, and then take the squared difference. And we take the sum, and we divide the sum by n minus 1. Okay, so with this definition, the corollary says that then xn bar and s squared, or probably I'll carry the n here. Yeah, this is a little different from my old notes, but I think it's better to keep the n here. So we are aware of the sample size. The sample size gets into play for both the mean and the sample variance. So these two things are independent. So this is another important result as a consequence of what we proved. So we basically said that, so when you have a set of random variables, IID, x1 to xn, you compute their mean, you compute their sample variance, and these two, right? Because they both of them are some operations, or we can say functions from your x1 to xn. So therefore, they inherit the randomness from uncertainty of x1 to xn. So they are random variables. And we say that they are independent. So again, a reminder of what independence means. It means that no matter what value this random variable takes, the distribution of the other random variable is unaffected. So they have nothing to do with each other. So to make a real world analogy, it's like if I say we have two students and their career choice decision at this point are random. They could go to grad school, they could go to work, right? So that's just a random decision. But when I say the two students' decisions are independent, it means that A's decision will not affect B's decision. So B's decision will be like that anyway. So that's just a way to understand what the independence means. And I think that this word is actually very connected to the dictionary meaning of independence outside of statistics. Okay, so this is the result, and we will use this result very soon, so you can see why it's useful. So basically, to prove this, I just need one line to say, since we just proved that xn bar and x1 minus xn bar up to xn minus xn bar, they are all independent. I should say x is independent of these things. Okay, so and Sn squared is a function of x1 minus xn bar and 2xn minus xn bar. By definition, it's just the sum of their squares and divide by 1 over n. Okay, so hence we can conclude that xn bar and Sn squared are independent. Okay, so because as I said, by the definition of independence, the value xn bar takes would not affect these n values, how they would take, what values they would take. So therefore, it will not affect those n values, so it will not affect the square sum of those n values, which is Sn Sn squared. Okay, so we will use this result very soon. Just bear in mind that here sample mean, sample variance are independent if the sample is random, is a random sample from standard normal. Because it's a random sample from a normal distribution, not necessarily standard normal. Okay, this is a corollary. Now we're moving to our next theorem. This is called the theorem 2. It's about this Sn squared. So this theorem says that based on our above definition, still under this normal assumption, IID, we will have n minus 1 times Sn squared divided by sigma squared. This thing will follow a chi-square distribution with n minus 1 degrees of freedom. Okay, so this is something we will use, and this will be something that serves as the basic for the most famous test probably in statistics called a t-test. And this is the foundation for t-test. Okay, why would this follow a chi-square n minus 1 degrees of freedom? So recall what I just said, right, as a recap of previous lectures. So we just said that for those x1 to xn, we take their standardized squared sum, right? I just wrote this. I said this follows chi-square n, right? This is what we have. And if I pull this out, this is basically, so the left-hand side is basically, I'll just write this, it's actually equal to, I can get sigma square out. It's the same sigma square. I put a sum in the numerator. Okay. And now I'm going to use a very important trick we will use in statistics. And this trick is that if you want to change the center of your square difference, then you can minus your new center, add the new center here, and keep this minus mu. So what I said exactly is that for, let me just do it. So inside the sum, you see now the center I need is by the definition of Sn squared is xn bar. So I need to do the subtraction of xn bar instead of mu. So what can I do? I can introduce minus xn bar into the square difference. So I can write as xi minus xn bar, and I will add it back plus xn bar, and finally minus mu, which is originally here. Okay, so do people understand this part? This is the key for us to introduce minus xn bar into the square. Okay. Okay, and then you see we're going to expand the square by treating. So we are going to treat this as one term, and we're going to treat this as another term to expand the square. So therefore, we are going to obtain xi minus xn bar square. That's the term we want. Okay, so let's continue. So then inside the sum, we would have xi minus xn bar square and the cross term plus 2 times xi minus xn bar times xn bar minus mu. Okay, finally, xn bar minus mu square. Okay, are people with me for this part? I'm doing nothing special, just to extend the square term. Okay. Okay, then let's try to simplify the sum. So first, we are going to get a term we want. So just going from here, let's see that given the Sn square definition, you can see that n minus 1 times Sn squared is indeed the sum of xi minus xn bar squared. So I already have that. So therefore, for the first term, I get it. And it's basically, I would say, I'll just write it directly. Okay, it's basically m minus 1 times xn squared, which is the sum of xi minus xn bar. I have it already. Okay, for the second term, I get a sum into each term, okay? Second term, I move 2 out of the sum. I can also move xn bar minus mu out of the sum. That's the key. The reason is that the sum is for I. I goes from 1 to n. And this xn bar minus mu doesn't involve I. So I can move it out of the sum for I. So I move it out xn bar minus mu. And the sum is only for the term that involves I. Okay. Sorry, my bad. Xn bar. Okay. That's the second term. And for the third term, it doesn't involve I. So it's just something not related to I added for n times. So therefore, it's just n times xn bar minus mu square. Okay, sigma square. I keep it. So what's left for me is to simplify this. So one thing to note is that, I'll just write here, for this sum I from 1 to n, xi minus xn bar, this term, if I write it expanded, you will see it's 0. The reason is that only the first term is involving I. So I put it sum xi. Okay. And the second term minus xn bar doesn't involve I. So it's xn bar added for n times. So I write as n times xn bar. Okay. And then you see by the definition of xn bar is the sum divided by n. So that's why they cancel. It's 0. This is an important fact that we will use for a lot of times, especially if you go to continue taking 100C for linear model, then you will use this a lot over there. All right, so because of this result, the second term becomes 0. So this one becomes 0. So why does it become 0 again? So because of the definition of xn bar, can you just try to write down the definition of xn bar on yourself? No? Okay, so xn bar is defined as 1 over n summation of xi. Did you see why now? Okay, yeah. So this becomes 0. And then we are just left with this term and this term. So we have m minus 1 Sn squared over sigma squared plus n times xn bar minus mu squared over sigma squared. We have these two terms. Okay, and one more thing to note is that we give you the recap about the distribution of xn bar. So recall with what we did in the beginning, that xn bar follows normal distribution with mean mu, variance sigma squared over n. Okay, so what does this imply? It implies that xn bar minus mu divided by sigma over square root of n. This is the standard deviation of xn bar. Would follow standard normal. Okay, and furthermore, this will tell me if I square it, xn bar minus mu over sigma over root n. If I take the square and simplify it, I would actually get sigma square n times x n bar minus mu. I just moved this denominator of denominator to the numerator. This would follow chi-square 1 based on what we learned. So therefore, this is exactly our second term. Okay, so we know that this term follows chi-square 1. All right. And we know the left term follows chi-square n. Then we're left to prove that this other term follows chi-square n minus 1, which is the conclusion we try to prove. So how do we do it? Again, we are going to use independence. You know, this one just involves Sn squared as the only random variable. This one only involves Xn bar as the only random variable. From the corollary we just proved, Xn bar and Sn squared are independent. So therefore, these two terms are independent. And that's the thing we need. Okay, so let's try to start from here. So now let me denote, try to simplify our discussion a little bit. I denote the left-hand side as my W. Yep, I'll call it W. Denote W as this left-hand side, sigma square summation xi minus mu square. And I denote U as the term I want to prove for its distribution. And I denote V as the other term. Okay, so I'll put this aside. So we know the following. We already have W follows chi-square n, V follows chi-square 1, and U and V are independent. This is what we have so far. So are people with me? Okay, so now we are left to derive the distribution of U. That's the thing. Oh, and also I forgot to say that W equals U plus V. This is the key. We have those four things. So now we are going to derive the distribution of U. And again, we are going to use the joint MGF that can be factorized as the product of the marginal MGFs. So we will say that because U and V are independent and because W equals U and V, so the joint MGF of, not joint MGF. So the MGF of W at T, any real value T, by the property of our by the independence property of MGF can be written as the product of the MGF of U at T times the MGF of V at T. Sorry, I should clarify, I made a mistake. This is not involving the joint MGF, but involving the sum of independent random variables MGF. So this is a property we gave you before. So that the sum MGF is equal to the product of the individual components MGF at the same T, evaluate at the same T. Okay, so now we are going to use the MGF of chi-square distribution, which we derived a while ago. And you also try this in your homework. Okay, so now we'll say that, recall that the MGF of chi-square distribution with n degrees of freedom is 1 minus 2t to the power negative n over 2. So this is the MGF we use to prove that if you have two independent chi-square distributions chi-square random variables with degrees of freedom m and n, then their sum will still be chi-square with degrees of freedom m plus n. We had this result before. So we would have just put the w's MGF, w is chi-square n. So we would have 1 minus 2t to the power n over 2. That's the MWT is equal to MUT times the V MVT. V follows chi-square 1. So this becomes minus 1 over 2. Okay. So from this, then we can derive that MUT, you just divide this to the left-hand side. You will have that this is equal to 1 minus 2t to the power negative m minus 1 over 2. Okay, so finally, we can say that, so we know this is the MGF of chi-square, and the degrees of freedom is just this numerator here above 2. So we will say U follows chi-square distribution with m minus 1 degrees of freedom. And we conclude this proof. Okay, so the whole idea is that we try to express this term, which is, let me just write this again. So this m minus 1 Sn squared over sigma squared is basically sum of xi minus xn bar squared over sigma squared. That's basically it. We try to express this term as the difference of this chi-square n term minus this chi-square 1 term. So the chi-square n term involves the standardized x1 to xn, and this chi-square 1 term involves the standardized xn bar. And their difference happens to be what we have here in our sample variance scaled by n minus 1 divided by sigma squared. So that's why we can finally prove that this is chi-square with n minus 1 degrees of freedom. And now you can also see that I would say this is the physical meaning of degrees of freedom. So by degrees of freedom, by the name, you can see it's about how many degrees can we freely change. Okay, so this term has n degrees of freedom because x1 to xn, they are all independent. So each one can freely change. So the degrees of freedom is n. Okay. And here, this xn bar has 1 degree of freedom because you already unite those n random variables by taking their average. So they become one thing, and that's 1 degree of freedom. So only one thing is changing. Well, this one, the one we're proving, has n minus 1 degrees of freedom. It's because you see here in the square sum, although the square sum involves n terms, each term can change, but they are tied to have the same. So x1 to xn are tied to have the same mean. So xn bar is tied. So that's why you lose the 1 degree of freedom by using the xn bar as the center instead of the mu. So that's why you have n minus 1 degrees of freedom. So this is just an intuitive way of interpreting degrees of freedom. Okay, so far, I think this is all I want to say about chi-square distribution. Again, a recap. For sum of n IID standard normal squares, it's chi-square n. But the sample variance, because we are using the sample mean as the center instead of the real mean mu, we lose 1 degrees of freedom, and we are at chi-square n minus 1 degrees of freedom. Okay, so this concludes this part about chi-square distribution. Do we have questions before we move on to our next topic? The next topic will be T distribution. Why the cross term becomes minus xxx? Where is the cross term?
Oh, the cross term is 2
You mean
multiply.
here?
Yeah, after the below line.
After this is the sum of xi minus xn bar.
Yeah, in the first line is positive. It's plus the
Oh, sorry.
cross term,
Okay,
and
yeah.
after
Okay, sorry. It should be plus. Yeah.
yeah.
Okay.
Okay, thank you.
Okay, yeah, because here this one doesn't matter that much because
Yeah.
it's 0. Yeah, thank you for pointing this out. Okay, so let's go to T distribution. It's our next topic. So it will rely on our chi-square distribution definition. So now we're going to define the T distribution. And it's defined based on 2 independent random variables. One is standard normal, one is chi-square. Okay, so let's say that let Z be a standard normal random variable and U be a chi-square random variable with n degrees of freedom, and Z and U are independent. Okay, so with this, so then how do we define the distribution of T distribution? How do we define the T distribution? Then the distribution of this random variable ratio, which is Z divided by U over N. So U is divided by N, is degrees of freedom. I take the square root, and Z divided by the square root is defined as the T distribution as Tn. I wrote this. So this is called the student T distribution with n degrees of freedom. So let me explain why it's called a student's T distribution. So here the student does not refer to you guys. It's not a real student. Instead, it was a statistician who worked in a Irish beer company. So I would say 100 years ago. So basically at that time, the question he faced is that if they have 2 ways of brewing beer and they want to compare which way gives the better quality. So in other words, they want to compare 2 batches of beer, each brewed in one way. And then it becomes a statistical question. Which one has better quality? So for that question, he invented the so-called, very famous, which is still used, the 2-sample t-test. And in the research paper he published for that test, he actually tried to hide his name, probably because I guess because of being modest or some reason, he just called himself a student. So that's his pseudonym. So that's why it's called student's t-test. So that's why this S should be capitalized, because it's not about any general student. It's about that specific pseudonym. Okay, so here we're not talking about 2-sample t-test yet, but this distribution, because of his invention, we give the name to him. So this one actually is the definition. So it's defined based on this construction. We have 2 independent random variables. One is standard normal in the numerator. One is chi-square n. We first divide it by the degrees of freedom n, and then take the square root and put the square root in the denominator. Then this ratio follows what we call the T distribution. And you may wonder why we want to take the square root, right? I think intuitively I can explain this way. Recall that we said a chi-square distribution is the squared version of the standard normal. So when we do the division, we hope the two things are in the same unit so that the ratio is meaningful. So to make them in the same unit, the chi-square distribution must be taken square root, because if it's not square root, then it's the squared form of the normal distribution. So they're not in the same unit. And also we know that the square of standard normal is chi-square 1 instead of chi-square n. And we know that chi-square n can be considered as n chi-square 1's sum, right? So therefore, to normalize this fact, we also divide this chi-square by n to make it more like chi-square 1 before we take the square root. So that's just an intuitive way of explaining why we divide the degree of freedom and why we take the square root. Okay, so this is called a Tn. This is the distribution notation. All right, what are the properties about this Tn? So let's say that properties of a random variable, now I denote it by big T, that follows this Tn distribution. So by property, we mean the mean, the variance, and what's the limit. Okay, so the first property is that the expectation of T is actually 0. So the Tn distribution is centered at 0. And the variance of T has this form n over n minus 2. So it's a little bigger than 1, but you can see that as n gets large, it's convergent to 1. So it becomes more and more like 1. And then finally, the limit. So as n goes to infinity here, the random variable T will converge in distribution to standard normal. So when the degrees of freedom gets large, this will essentially become a standard normal random variable. Okay, so therefore, to give you some intuitive understanding of the T distribution, let me draw the PDF of Tn. Okay, this is 0. And so basically, and this is the density as the y-axis. So basically, the PDF of Tn, when n is small, I'm also going to do the contrast, is actually pretty heavy tail. So by heavy tail, I mean that if I compare this to this curve, so if this is the standard normal PDF, what it means is that at any value away from 0, then the tail probability of Tn is bigger than the tail probability of standard normal. So in other words, standard normal is more concentrated around 0 than Tn. So Tn is more heavy-tailed than standard normal. So you have a larger probability away from 0. Okay, but when n is getting large, say n is getting large. Okay, still the same two graph. Let's say this is 0. And I have the standard normal plotted first. Then in this case, the PDF of Tn will get closer to the standard normal. So it may become something like this. Something like that. So just become a little more slightly heavy-tailed, but much similar to standard normal. So basically, the direction of change is that when n gets large, the curve will be squeezed towards 0 and become a standard normal curve, density curve. So that's what happens with the Tn distribution. Okay, so that's the introduction about the T distribution. Do we have questions about it? It's symmetric around 0, unlike the chi-square one. under like the chi-square n distribution. Chi-square distribution has values taken on the positive part of the real line, but this is for the whole real line, just like our normal distribution. And its shape is also bell-shaped. All right, so then I'm going to introduce another theorem called Theorem 3. So this one is saying that, again, in our normal IID scenario, let x1 to xm be IID normal distribution with mean mu variance sigma squared. And again, let's define that, xm bar. We defined this before. I'm going to write it down again. And Sn squared. Okay, so xi minus xm bar squared. So then with this, the conclusion is that then xm bar minus mu divided by S over root n. This would follow T distribution with n-1 degrees of freedom. Okay, so this is the conclusion, a very important result. And this is the result we are going to use for what we call one sample T test. So maybe I'll try to first prove this first and then give you the application of this. So we will just prove this using the definition of the T distribution. So we are going to show that the numerator is some standard normal, denominator is some square root of chi-square divided by degrees of freedom. That's what we want to show. So from our previous theorem, the one we just proved, from theorem 2, we have n-1 times, Sn, I dropped it, Sn squared over sigma squared follows chi-square n-1. We had this. Okay. And we also have xm bar minus mu over sigma over root n. If you recall, we have this. The standardized as xm bar follows standard normal. Okay, then you see we have the two components we need for a T random variable. And these two things are independent. And xm bar and Sn squared are independent. This is from the corollary we did in today's class. Hence, we can construct a T statistic, right? So we take the standard normal in the numerator, xm bar minus mu, right? We take this in the numerator, and we take the chi-square 1 in the denominator. n-1 Sn squared over sigma squared, right? We had this, and we need to further divide this by the degrees of freedom, which is n-1. Okay, hence this would follow Tn-1 by the definition of T distribution, which we just defined. Okay, now we are left with simplifying this left term. And this term, you see, in the current denominator inside the square root, n-1 and n-1 should be canceled, right? So I keep the numerator, xm bar minus mu, sigma over root n unchanged. But in the denominator, n-1 will become an Sn squared over sigma squared after the square root will become Sn over sigma. It comes out like this. Then I further simplify it. I put this root n to the top, xm bar minus mu sigma. Okay, dividing this is equal to times sigma over Sn. or probably I keep this. Okay, maybe let's do this. Okay, so then I have root m xm minus mu. That's it. So it's the same as what I have here. It's the same as I have here. So I can divide root n to the bottom, that's fine. Xm bar minus mu, sorry, Sn over root m, that's it. So that's done, I'm done. So we proved that this ratio follows t n minus 1 just by the definition of the t distribution. And by the way, this symbol means that we concluded the proof. So with this, then what's the application of this? So this is the foundation of what we call one sample t-test. So let me put it here. Application in statistics called one sample t-test. So I don't know how many of you have heard of hypothesis testing, but I think this is something that should have been covered in the introductory stats course, like our stats 10, stats 13 here. So this one sample t-test is actually about this question. So let's say that we have an IID sample as we are setting IID from a normal distribution with mean mu, variance sigma square. And our question is this mu 0 or not? So the null hypothesis is that mu equals 0. Or it could be mu equals to some constants you specify. So maybe I can just say that mu equals C. Okay, C could be 0 or non-zero. Versus the alternative hypothesis is that mu doesn't equal to C. We want to do this test using the sample we collected. So, the component of the test, which we will cover in detail later in this class, is that we need to have a test statistic which summarize our sample. And here the test statistic is T. And the test statistic called T is defined exactly as this way. So xm bar minus something. Here I'm using this C as my mu, minus C, the mu under my null hypothesis, dividing Sm over root m. This is test statistic. So why do I define this way? It's because I want this test statistic to follow some nice distribution under the null hypothesis. And I know that under the null hypothesis, when mu is equal to C, this test statistic follows T distribution with n-1 degrees of freedom. So with this, then I can evaluate how likely I'm going to observe test statistics beyond my observed value, like values more extreme than my observed value. So let's say that based on my current sample, say the realization of T in our observed sample is, let me denote it by this T star. Okay, this is our observed value for this T. Then I want to know how likely am I going to observe this T, observe values equal or more extreme than this T star if my data were actually from the null hypothesis. So the p-value definition is basically the probability I'm calculating under the null hypothesis that my T is more extreme than this. So basically, the absolute value T is greater or equal than the observed T star's absolute value. So that's how we're going to calculate this. And so then, this becomes the two tails in the T and -1 distribution. So to do this, it becomes like if you draw the T, and this is 0, this is the PDF of Tn minus 1. So let's say that and this is the distribution of T star under the null. Let's say that my small T star lies here. So its absolute value is itself. So for T greater or equal than its absolute value, the probability is actually these two tails. So these two tails together is the p-value I would get. So sorry, I draw the back leap, but it should be symmetric. And they're supposed to be symmetric. So that's how we do it. So in other words, hypothesis testing will require the null distribution of our test statistic. So it's a way to just to justify whether this T star, assuming this null is true, is our T star really an outlier? If it is, then we will tend to reject the null because we think it's unlikely to observe this T star from the null. So we reject it. So it's that reversed way of thinking about hypothesis testing. Given our data, which gives us T star, we are imagining other possible outcomes, other possible realizations of this T under the null. And these other possible values is described by this null distribution, Tn minus 1. So you see, this theorem 3, gave us a foundation to derive the null distribution of T. And that saves us a lot of trouble because, in a traditional textbook, you will be able to have a table for this T distribution given the degrees of freedom. And you look it up and you try to find the tail probability. That's your p-value. Okay, so if this is something that's hard to understand for now, it's okay, because we will talk about hypothesis testing in detail later in the class. I'm just trying to give you a primer here so you know why we need this theorem. Okay, so since we have 3 minutes left, so I will start the definition of the F distribution. This will give us the foundation for our later discussion. So we have T distribution constructed from standard normal and chi-square, and we are going to construct another distribution called F distribution. Okay, it will be constructed from 2 independent chi-square random variables. So let's say we have U follows chi-square M, V follows chi-square N, and U and V are independent. Okay, then we define the distribution of this ratio. So U divided by N over V divided by M. So each one is divided by its degrees of freedom first before I take their ratio. Is defined as, we denote this as the F n comma N. The F distribution with M numerator degrees of freedom. So it has 2 degrees of freedom, 1 numerator, 1 denominator. With M numerator degrees of freedom and N denominator degrees of freedom. This is it. So this is the key, the M and N. Okay. So a homework question you will have this week is actually a very straightforward question, but it's testing your understanding. So the question is that if I take the inverse of this ratio, is it still an F distribution? If it is, then what are its numerator degrees of freedom and denominator degrees of freedom? So now you can start thinking about this based on the definition. Okay, so this is the definition, and I think we can stop here. So next time we'll talk about more about this F distribution and its related F test. So the F test will allow us to compare two samples in terms of their variance, whether the two samples share the same variance or not. Okay, again, I'm going to give you the theory first, application as a primer, because we're going to talk about hypothesis testing formally later in this class. Okay, so I'll see you on Wednesday. Bye.